Okay, great. So, hello everyone. For those of you who couldn't take part in the previous session, I just wanted to say that you can find the recording and the notes on Canvas. Everything is published there. And another thing that I just want to say here is that as soon as you have a question, please ask in the chat or unmute yourself and just ask normally, and I would be happy to answer. Okay, so as I said in the previous session, at the beginning of this course, we're going to talk mostly about basics of cryptography and some cryptographic primitives. And we actually started this with cryptographic hash functions in the previous session. And today we're going to go a bit deeper into hash functions. And then hopefully, if we have time, we will see some other primitives as well. So let me just recall the definition that we had. So let's say that sigma is our alphabet, in this case 0 and 1. A hash function is simply a function that takes a string of any length and outputs a string of a fixed size n. And we talked about the fact that no hash function can be one-to-one because the domain is infinite and the codomain and range are finite. But we said that in order for a hash function to be useful for our use cases, and generally in cryptography, what we mostly care about use cases in cryptocurrencies, it has to have three different properties. The first property was that we want our hash function to be collision resistant, which means that we shouldn't be able to find two different inputs x and y that hash to the same value. So we shouldn't be able to find two inputs x and y such that h of x and h of y are the same. And we talked about what we mean by this. We mean that there is like no efficient algorithm that can find it in a reasonably short time, and a reasonably short time in this case is the lifetime of the universe. And we also talked about the hiding property, which was this property that if someone gives you a value, you shouldn't be able to invert this hash function. So if I give you some value y, you should not be able to find an x such that when we hash x, we get y. Or in other words, you should not be able to find h inverse of y. The third property was something that we will come back to when we cover more advanced topics such as proof of work. I just wanted to mention it here so that you know that we will later on need another property for our hash functions. And as I told you before, we're not going to really talk about how we build hash functions because that's not really in the scope of this course. Instead, we just agree that such functions exist. That's good enough for our purposes. And especially one of them, the one that is often used in Bitcoin, is SHA-256. Okay. Then we talked about some applications, and actually I could only cover one application in the last session and didn't have much time to go deeper into it. So let me just do this again. Suppose that we have a huge number of files, and suppose that all of our files are also huge. So I have a set big F of large files. And now someone gives me a single large file, small f. And the question is this file in the set of files that I have seen until this point? And the main idea here was to use the hashes as some sort of a digest. So something's wrong with my tablet. Okay. So the idea is to use hash as a digest. So instead of just comparing every single one of my files with this new file, I just take the hash of the new file and I have the hashes of all the previous files, and I just check if this hash is in the list of hashes or the set of hashes that I have. And we talked about why this works. We are basically using the collision resistance property, and the idea is that if I have a file f prime and the hash of f prime is the same as the hash of f, but f prime is not itself the same as f, I've basically found two inputs to my hash function that have the same output. So I found a collision. And the idea was that this should be really hard. So we assume we can't do this. And so this idea of using the hash as a digest doesn't really lead to many false positives. Well, actually, in practice, it doesn't really lead to false positives at all. But it makes our life much easier because instead of comparing huge files, we just compare small hashes. And again, remember that the input strings, which are our files in this case, could have any lengths, but our hashes have a fixed length. So it's much easier to work with the hashes. So sorry, that was the idea for comparing files. And actually, this is what most torrent services do as well. So if you want to download a file from a torrent, you will usually just know the hash of the file that you want to download, and that's how you can search for it. Okay. But the second application is actually the one that I want to talk about today, and it's much more interesting for us because it relates very well with the ideas of cryptocurrencies. So here's the scenario that I have. So suppose that you don't trust your bank. Let's say that you have your bank here, and the bank has a list of transactions in your account. So this is the list of transactions that have happened on your account. So you have a transaction 0, transaction 1, transaction 2, so on. Maybe you have many transactions. And let's say that this is a scenario where we have normal banking. So you don't keep track of your own transactions. The bank does that, and it gives you a statement maybe every time that you add a new transaction, or maybe it gives you a statement every month or at any interval that you like. Now, the problem here is that suppose you don't trust your bank. You don't trust that your bank will not change these transactions. So you want to be sure that after the bank told you about some transactions, for example, after the bank told you the first 10 transactions, then it's impossible for the bank to change them without you knowing about it. Okay? Now, how can we do this? Well, one way of doing it is to just store all the transactions that the bank tells you about. So every time you get a bank statement, you keep a backup of it, and every time you get a new bank statement, you cross-check with all the previous ones to make sure that no transactions in the history have changed. But the question is, can we actually do this in a better way using hashing? Okay, so the scenario that we have here is, again, if I just want to write it down, you do not trust that your bank will not change the history of your account. Any ideas? If you have any solution in mind, please write in the chat. Okay. So again, the problem here is that we don't want to do too much work. We don't want to have to constantly check the history to make sure it's the same as every other history that we have seen until this point. So the simple solution that we have here is to just use a linked list. So let's say I create a linked list, and this is my transaction 0. Then this is my transaction 1, transaction 2, and so on. And each transaction has a pointer to the previous transaction. Okay. And then I have transaction N here, which has a pointer to the previous one. Now, if the bank wants to add a new transaction and an n plus first transaction, then it has to add it here, and it has to put a pointer to the last transaction that you have seen, which is transaction n. But we can't really use normal pointers here, because suppose I just have normal pointers, maybe the bank changes this pointer here and just points directly from transaction 2 to transaction 0. How would I know that the bank has changed that? I wouldn't be able to know that, right? But instead we can use something else. Yes. Yeah, in the chat we have a bunch of solutions that are nice. Actually, there is some delay in the chat, I think. Yeah, so someone says hash every transaction. That's correct. The other one says store a hash of each transaction that takes input of last hash, right? Right, correct, yes. So all of you have the right idea here, but let me just formalize this right idea that is in the chat. So the idea here is to use the hash as a pointer. Okay, so we have seen the use of a hash as a digest before, but now we want to use it as a pointer. What does this mean? This means that when I say there is a pointer in transaction 1 to transaction 0, this pointer does not actually point to transaction 0 in some kind of memory or anything. It just stores the hash of transaction 0. So this pointer is simply the hash of transaction 0. Okay, so if I zoom in on my transaction 1, this is what transaction 1 looks like. So it has some data, which is like transfer of some X amount of money from some person P to some person Q, let's say. And then, so this is the first part of the transaction. And then in the second part of the transaction, it has the hash of the previous transaction. Okay. And generally, if this is transaction N, it will have the hash of the previous transaction, transaction N minus 1. So these are the two things that I will have. This is 1, this is 2 in my transaction. But conceptually, I think of this hash as a pointer. Why? Because if, again, I just save the set of all transactions in my memory, and someone gives me a new transaction, and this transaction has the hash of one of the transactions that I have seen before, I can easily search for that hash in the set of hashes that I have, and I can easily find the previous transaction. So this hash pretty much works like a pointer. Okay. So let me see. There is a question that asks, shouldn't it point to the next transaction? No, well, because you see, the thing is, transaction 0 happens before transaction 1. So when we create transaction 0, we don't know anything about transaction 1, so we don't have the hash of transaction 1. And we can't make transaction 0 point to transaction 1. But when we make transaction 1, we already know about transaction 0, and we can just compute its hash. Okay. Now, let's see what happens if we use this solution. So whenever the bank wants to add a new transaction, let's say I have some new transaction here, the way that he adds it is that it just announces this new transaction to you, and you as the customer verify that this transaction has the hash of the very last transaction that you have seen. So you verify that it points to the last transaction that you have seen, right? And that's all. You don't have to verify anything else. Why? Well, first of all, you can be sure that this transaction is added in the right place, right? Because you can make sure that it's really added to the end of the list, not somewhere in the middle. That's just checking that the hash pointer is to the last transaction. But you can also be sure that nothing in the middle gets changed. Because suppose that the bank wants to change some transaction. Let's say the bank is malicious and wants to change transaction 2. Okay. Any change in this transaction 2 will change its hash. But now transaction 3 has to point to transaction 2. So transaction 3 should change because it should have the new hash of transaction 2. But this also changes the hash of transaction 3. So the bank now has to change transaction 4, which points to transaction 3. And this goes on forever. So if the bank wants to make any changes here, if it wants to tamper with the history, you will easily know because it just can't do it without changing every single transaction that comes after that point. Okay, so one question is, so we have to traverse the whole linked list each time to make sure nothing gets changed in the middle? No, that's the beauty of it. So you just check one thing, you just check that this new transaction is added to the end of this linked list. So basically my point is that as long as you just keep track of the hash of your last transaction, you can be sure that nothing fishy is going on, because if the bank changes anything in the middle, the hash of the last transaction should also change. So the bank cannot convince you in any way to change your sequence of transactions, and any change in any point will have to change all the pointers after that point. So you can easily figure it out because you will see that the hash of the last transaction has changed. So again, the way you should think about it is that the bank gives you a statement, let's say every month, and this statement has all these hashes in it. And you just have to check the last hash. Okay. So there is a question that asks, is transaction n+1 the hash of transaction n? Not exactly. So each transaction is of course a transaction because it has some, that's in the name, right? By definition, it should transfer some money between some people. For example, either it pays something to you or it takes something from you. But other than that, we will also include a hash of the previous transaction. So transaction n is not just the hash of the previous transaction, it's the hash of the previous transaction plus some extra information that we need. Okay. So another question is, how can we guarantee that the linked list does not break in the middle? Well, this is just by making sure that every time that a new transaction is announced to you, every time that the bank announces a new transaction, this new transaction points to the last transaction that you have seen. So again, you always just keep track of the hash of the last transaction that you have seen from your bank and accepted. So if every transaction that is added just points by hash to the very last transaction that you have seen, you can be sure that you just have a linked list and there are no forks or anything in between. Okay. So another question is that, is the hash provided by bank or ourselves? That's again the nice thing about this. So you just have to fix some hash function. Let's say you and your bank say we use SHA-256, and then anyone can compute their own hash, right? So the bank will just give you this new transaction that is going to be added, and you can compute its hash on your own. And you will, of course, get the same value as the hash that the bank computes because you both have the same transaction, you're both using the same hash function, so you will both get the same result. Yes. So the point here is that basically you don't have to verify the whole history all the time. And instead, you just have to verify one hash, the very last hash. That's the main idea. And it makes life much easier for you. Okay. So another question is, how often will the hash function go wrong? I don't know what you mean by going wrong. The hash function, will go wrong. It will not go wrong, right? It's a function and you can easily compute it. And it also has those properties that we talked about. Okay, so let's actually do, duplicate result. Yeah, we will not have a duplicate result because we are assuming that the hash function is collision resistant. So actually, let's do that analysis. Let's see what an attack looks like and why this is safe. So an attack by the bank is any attempt to change the history. So let's say the bank wants to change, let's say, some transaction I. Okay, this is the attack that we want to make sure will not happen. So what does this mean? This means that we have these transactions and each one is pointing to the previous one with a hash pointer, which basically means that it's just saving the hash of the previous transaction. And at some point I, the bank wants to change this. Okay, but the bank has already given you all of these transactions. Let's say we already have n transactions like this. This is the last transaction that the bank has given you, transaction n. And now let's say that the attack is that the bank wants to change transaction I. Okay. So again, remember, what are you keeping track of? The user is keeping track of the hash of the last transaction. Hash of transaction. So if the bank wants to make a change at some transaction I, in order to avoid detection by the user, the bank has to do this in a way that the hash of the last transaction remains the same. Right? So, and here I'm assuming that the bank only wants to change this one transaction, but later on we will talk about any other change. So let's say that the bank changes this transaction, right? But the hash of this transaction will change. And the only way for the bank to make sure that the hash of this transaction does not change is that the bank should find another transaction, let's say transaction I prime, such that it has the same hash with the current transaction, right? So if the bank finds some other transaction I prime, such that it has the same hash of transaction prime I is equal to the hash of transaction I, then it can replace this transaction with the new one. Right? And everything will go through. But the problem here, tx prime. But the problem here is that, well, our hash function was collision resistant. So the bank cannot find two different transactions that have the same hash. Okay, so let's say the bank doesn't do this. Let's say the bank just changes transaction I to some other thing, to transaction I prime, and tries to fix it at the next transaction. Let's say it tries to fix it at position I plus 1. But then again, it will have the exact same problem. It has to find a new transaction that has the same hash, and so on and so on. Another way to look at it is to look from the right side back. So let's say I have the hash of my last transaction, right? This transaction points to the previous one. That one points to the previous one, and so on. any change in any of the hashes has to change all of these hashes. But what I know for fact is that I'm keeping track of the last hash. So any change in this whole linked list will not go unnoticed unless the bank can find a collision in my hash. And we assume that the hash function is collision resistant. So the bank cannot find a collision. So the bank cannot fool us. We can always keep track of the last transaction, of the hash of the last transaction, and be sure that nothing else can change in the history. Okay, so let me just write it here that this applies to any change in the history. So it's not just if the bank wants to change a specific transaction, but any kind of change in the history would have the exact same effect. Okay, so let me just look at the questions one more time. So one question is that what if the bank remembers the hash value and changes something in the history, but forges the value artificially as the true value? Well, again, the bank cannot do this because we are assuming that the hash function is collision resistant. So the bank cannot change anything without changing the hash value as well. So it's impossible to make any changes without changing the hash. And we are keeping track of the hash. So if the hash changes, we will just say, okay, this is not acceptable. So one person asked, what exactly is TXN? So we generally, well, we write TX as a shorthand for transaction. So when I write TXN, I just mean transaction N. And I don't care how exactly you save transactions and what data you save in them. So it can be, for example, a transfer of some amount of money from some account to some other account. What I care about is that it should have the hash of the previous transaction. So here, I'm not really concerned about what exactly the transactions do. The only thing that I'm concerned about is that I want to be sure that the bank cannot change the history that it has already shown.
Professor, I was just trying to ask, what if it's the last transaction? Like, because none of the hashes are pointing to that transaction hash.
Right. So you are still keeping track of the last transaction, right? And its hash. So
right.
Whenever the bank gives you a new transaction, the idea is that you can just compute its hash, right? So even though there is no pointer to it, you have computed it the very last time, you have computed the hash the very last time that the bank has given you that transaction. So you always know the hash of the last transaction. And that's actually the reason why you have to always keep track of this hash. So this is the only thing that you have to keep track of because it's not found anywhere else in the data structure.
All right.
The hash of the very last transaction, yeah. Okay. Okay, another question is it not possible to accidentally bump into two transactions with the same hash? Mathematically, it's possible, but in practice, the probability is so low that it has never happened. So again, think of your hash function. Let's say your hash function outputs, I don't know, strings of a fixed length. So let's say the length of the string is 1024, for example. It's very unlikely because you have 2 to the power of 1024 different possibilities for the output of your hash function. So it doesn't really happen that we just bump into it. Okay. So another question is, would it be easier to manipulate transaction N because not, oh, okay, I answered this one. Another one asks, do you have a function that constantly checks if the linked list is not changed or broken? No. So the only thing that I check every time is that the new transaction that the bank is announcing to me points to the very last transaction that I already know. So if I already had, let's say this transaction, I also know its hash. right? And the only thing that I always check is that whatever new transaction the bank claims points to this previous transaction, so has the right hash of the previous transaction in it. And this is enough to make sure that the chain is unbroken. And again, this is the whole point. We don't want to check the whole chain. We don't want to check the whole linked list. We want to be able to just check one hash at the very end and be sure that nothing has been tampered with. So another question is, what if they just change the pointer to some other transaction and break the linked list in the middle? So we just don't accept that. You see, the bank gives you a list of transactions, and if the bank gives you a transaction that points to somewhere in the middle and not the last transaction, you just tell your bank, this is not an acceptable transaction. I'm not accepting this. Okay. Another question is that as the transaction linked list gets longer, why is it impossible to find the hash value that's duplicated and swap it? It's impossible in practice. Well, but mathematically, if you think about it, the number of possible hash values is bounded, it's finite. So if the chain gets longer than the number of possible hash functions, possible hash values, then of course you will have a duplicate. But again, the number of possible hash values is something like 2 to the power of 1024. So that will not happen in practice. Okay, another question is, what happens if you change one transaction but also change other things? Well, the nice property here is that when you change these things, you have to do the changes all the way until the end of the chain, until the end of the linked list. And the user is always keeping track of the hash of the very last transaction. So the whole point here is that if the bank makes any change at all, anywhere in this chain, then it has to change the hash of the last transaction. And that's something that the user will easily figure out because they have the hash of the last transaction. Okay. So there are some questions about how to check if a transaction is valid. We don't talk about that right now. So our problem here is just to make sure that the history has not changed. So we might have some other rules for why the transactions are valid or not, but that's not our setting here. Our setting is just that we have a bank, we are the customer of this bank, we get a bunch of transactions. We want to make sure the bank doesn't lie to us about the history of transactions. Okay, and there are some questions. Do we have the right to change the previous transaction? Again, these are not really things that we care about right now, because this is just a solution to make sure the bank doesn't change the history. So that's the only thing we want to think about here. Okay, so this is actually an idea that is very much used in blockchains, and we will see it over and over again. But the main takeaway that I want you to have here is that we can use the hashes as pointers. So instead of pointing to something in memory and say where in the memory this item is located, we can just use its hash and say, I'm pointing to the item that has this particular hash. And that item can be a file, it can be a transaction. Later on, we will see that in Bitcoin, it's a block of transactions. And this is a very successful and very powerful idea, using hashes as pointers. And the main reason for its power is that when you use a hash as a pointer, you can be sure that the place you're pointing to cannot change without changing the pointer as well. So it's kind of a pointer that also gives you a guarantee of immutability, a guarantee that the item I'm pointing to cannot change without also changing the pointer. Okay. So, okay, let me just answer one more question when then I'll go to the next one. So someone asked, how are we going to make sure that transaction N is really pointing to transaction N-1 if it is all run by the bank? Well, because we always keep track of the hash of the last transaction. So when transaction n is added, we know the hash of transaction n minus 1. And we can just go and check the pointer in transaction n and see if it's actually the hash of transaction n minus 1 or it's something else. If it doesn't match the hash of the previous transaction, we just throw it out and we don't accept that transaction. Okay. Again, the idea here is not that the bank cannot change anything. The idea is that if the bank changes something in the history, we can figure it out and that we can basically detect fraud. Okay. And it's immutable in that sense. Like the bank cannot change anything without us finding out about it. Nice. So this was the idea of creating a ledger with hash pointers. Let me now go to the next problem that we want to talk about today. And this is the problem of commitment schemes. So here's what I want you to imagine. I want you to imagine an auction. So let's say that I want to sell, let's say, a piece of art. And there are different people who want to make bids on it and tell me how much they're willing to pay for this piece of art. And whoever bids the highest will win the auction. But we want our auction to be blind. We don't want any of the bidders to know the bid of anyone else, right? So the way it's done in the real world is that all the bidders can just write their bids on a piece of paper and put it in an envelope. And we take all the envelopes together, we open all the envelopes, we see the values that are written, and we just take the maximum and say, hey, this is the winner. So everyone can see the bids of everyone else, but only after they have made their own bids, not before. Right? So everyone puts their envelopes on the table and only then all the envelopes are opened. Now, suppose that we want to do this, let's say, over the internet. We want to do this digitally. How can we do this? Okay. So here's the exact scenario that we have. Let me be a bit more formal here. Let's say that n people are bidding for an item. And let's say that person I wants to bid BI. Okay. And the requirements is that no one should know anyone else's bid before making their own bid. The other requirement is that everyone should be convinced that the highest bid wins. So everyone should see all the bids at the end of the process. And again, this is to ensure the highest bidder has won. Okay. So basically what we want to do is that we want to mimic or simulate this idea of putting the bids into a sealed envelope. And we want to do it again with hashes. And when I say it like this, you can easily see the solution, right? So the solution is that everyone can just announce the bid of their hash instead of, the hash of their bid instead of the bid itself, right? So here's the solution. So we say that in step 1, each player I announces the hash of BI. Okay, we will come back to this. And then after everyone did this, after all hashes are announced, then we have step 2. And in step 2, each player I announces the actual bit. And when I say announces, just imagine that we have some sort of a forum and they can just make a post online on it so that everyone can see what they're announcing. Okay. So what happens here and why is this something that actually works? So if you think about it, we wanted to have 2 properties. First of all, we want to make sure that no one should know anyone else's bid before making their own. So in step 1, the players are just announcing the hashes of their bids, right? And they're announcing it in no particular order. So a player that announces the hash of his own bid might already know the hash of some other player's bids, right? But one of the properties of a hash function was that it's hiding so that we cannot invert it. So the idea here is that even though we know the hash of the other player's bits, we don't know their actual bits. So we have this first property. So let me actually give these properties names so that I can talk about them in more detail. So let's say this is property A and this is property B. Okay. So in the analysis, we say that property A holds because the hash function h is hiding. So when player j knows hash of the bit of player I, so when player j knows hash of the bit of player I, he or she cannot know BI itself, because the idea was that we shouldn't be able to invert our hash function. Okay, there is some caveat here and I will come back to it. But this is basically the idea. So when I'm doing this, when I'm seeing the hash of the bits, they're not giving me any information about the actual bits themselves. So the second property is that everyone should see all the bits at the very end. And well, in step 2, we already have this because at the end, everyone has announced their own bit. So everyone can see all the bits, right? And let me actually add the step 3 here, which just says the highest BI wins. I'll come back to the questions a little bit later as soon as I'm done with this. Okay. So, but we also need a third property here, which I'm going to add. And the third property is that no one should be able to change their mind. So, and that's the whole point here. If you look at it, when the player I announces the hash of the bid, that's kind of committing to that bid, because now everyone knows the hash. And if later on the player announces a bid that has an invalid hash, that would just be ignored. Okay. So part C is that no one can change their bid. So again, so here after each player announces their bid, every other player can just take this hash and make sure that it was the same hash that was announced in step 1. And if this hash does not match the hash that was announced in step 1, we just ignore it. And we say, okay, this player has lost because they didn't follow the protocol properly. Okay, so here we say every BI with a hash that does not match step 1 is ignored. Okay, so now let's again go through this. So in the first step, everyone is announcing their hashes, right? These hashes do not give other players any kind of information about what the actual bid is, but it kind of commits us to our bid. We can no longer change our bid. Because if we change our bid, then later on when we announce our bid, everyone else can just hash it and see that we were cheating. So that's the role that these hashes play here. These are basically what we call hashes as commitments. And that's why I'm calling it a commitment scheme here. So the role of step 1 is basically the same role as the envelope. You are putting your bid in an envelope. In this case, the envelope is the hash function. And what that means is that you can no longer change it. But at the same time, no one else can see it because it's already hashed. Others can only see it when you actually announce it later on, but they can check. They can hash what you announce as your bid and check that it was actually the same bid that you had committed to. So property A is satisfied because the hash function is hiding. So when you announce your hash, no one else is able to understand what your value was based on the hash. Property B holds trivially because at the end, everyone is just announcing their bid. And property C holds. So you see, property C was that you shouldn't be able to change your bid. So if you change your bid, you have to do it in a way that doesn't change the hash. Otherwise, your bid will be ignored, right? So the only way you can change your bid is if you can find some sort of collision in the hash function. And unless you find a collision, you cannot change it. So property C holds because of collision resistance, because we assume that our hash does not allow anyone to find the collision. Okay. So there is just one caveat here, and the caveat is this. Suppose that this item that we're going to sell is something that is worth between, let's say, $0 and $100, right? If this is the case, then the bids of everyone is going to be something between 0 and 100. So there are finitely many different possible bids. What an attacker can do in this case is that he can just compute the hash of all the possibilities from $0, $1, so on to $100. And whenever someone makes a bid and announces their hash, they can just look into the list of all the possible hashes and say, okay, this person has bid $99, for example. So we want to make sure that this is not possible. And in order to make sure that this is not possible, we have to make our domain larger. So it shouldn't be the case that the number of choices that the players have are only 100 possible choices so that someone can just brute force it. So what we do here is that we just add another step, very simply, step 0. And what we say here is that each player I chooses some random number. And we usually call these random numbers nonces. Chooses a nonce let's call this, since it's a nonce, let's call it Ni. So this Ni is like a random large string, or a random large number. We don't really care if it's a string or a number. Okay, so each player just chooses a random nonce, which is some huge string. And instead of announcing the hash of his bit, the player announces the hash of the bit and the nonce. And what I mean here is that I'm looking at these two things as bi and ni as strings, and I'm just putting them together. I'm appending them to each other. Okay? And I can have some sort of separator here in between as well, just to make sure what's the bit and what's the nonce. Okay, so I just write my bit first, then I put a space, and then I write my nonce. This gives me the string, and then I hash this string. And here, when I announce my bit, I also have to now announce my nonce and the nonce ni. And then others, when they want to check, they have to basically hash both of these together again to make sure that the hash matches and I haven't changed my bit. Okay, so this is just a trick to make sure that the domain is big enough that we can actually have unpredictable hashes so that people cannot just brute force every possibility. And that's it. This is the protocol. Now I'm going to answer the questions. And by the way, we are out of time. So this is the end of this session. You can leave if you like to. I'm going to answer all the questions in the chat, and then I will leave as well. Okay, so let me see. Okay. One question is that, does this need to be verified when they make the announcements by performing the hash again? Yes. So the way this works is that in step 1, everyone announces their hashes. And in step 2, when they announce the bit and also the nonce, then everyone else computes the hash. Everyone else computes the hash of this bit and this nonce and makes sure that the hash actually matches what was given in step 1. And if it doesn't match, then everyone agrees that this person is a loser. They didn't follow the protocol, so they're not going to win the auction. Okay. So another question is that if we use SHA-256, can I just hash every number so that I know all the possible hashes to match? Yes, this can be done. And of course, it can be done if the total number of bits is small. And that was the reason why we added this nonce thing to the end, so that the number of possibilities for the string that is hashed becomes huge, so that no one can do this kind of attack. Okay. We have another question about trying every possibility, which I answered. Okay. Yes, the nonce. There are a lot of questions and answers that are basically the things that I covered. That's nice. Okay. Okay, if the information added is public, one can also try all possibilities by including that information. If it is not public, no one will be able to verify the bit. So this nonce or extra information that we add will be made public at the end. But the point is that no one can try all the possibilities, because let's say this nonce is, I don't know, again, at 1024 bits long. So make the nonce long enough so that no one can check all the possibilities. Okay. And by the way, we usually also just fix a length for the nonce. We say, for example, use a 128-bit nonce or use 1024 bits, something like that. Because we don't want the protocol to be too complicated. If people can have any lengths of nonce, then at this step, they might just announce a huge NI and it would be hard for the network and for others to compute the hash. So we'll fix a length, but we'll fix a large length. Okay. So when does a bidder get to see other hashes? So this is the order that things happen. So in step one, as soon as a player announces his hash, every other player or every other bidder will see their hash. Okay, but the only property that we want to have is that everyone sees every other hash before actually announcing their own bid and then nonce. Okay, someone asks about the waitlist students who cannot access Canvas, apparently. Okay, I'll check this and I will add everyone on the waitlist to the Canvas. There's a question about class quota. Will it be increased? I don't know, and it's actually very unlikely at this point that the class quota gets increased. But if you are close to the top of the waitlist, it's very likely that you will get in, because probably some people will drop. Okay. Okay, if you missed the first lecture, you can see it on Canvas, and I will give access to everyone on the wait list as well. Don't worry about this. Okay, someone asks, should everyone use the same hash provided by hosts, or can they choose a different hash by themselves? So we don't really have a host here. It's a very decentralized algorithm, if you think about it. All the participants are equal. Like, everyone does the same thing. Everyone announces their nonce at the same time, and everyone sees other people's, everyone announces their hash at the same time and sees other people's hashes, and then they announce their nonces and so on and bids. So there is no particular person who is a host, but yeah, we just assume that everyone is using the same hash function. And again, usually in Bitcoin, for example, we use SHA-256. Actually, Bitcoin applies SHA-256 twice. But anyway, there is this idea that we agree on the hash function and we will just use a standard hash function. If people use different hash functions, then this wouldn't work, of course. Okay.
Professor?
Yes.
I have a question. You said that everything is decentralized. So how do they initially, who initially sets the hash function? Like, how do they choose which hash function is suitable?
Yeah, so in this case, we just assume that they have already chosen one. So in case of Bitcoin, Satoshi Nakamoto just published a paper and said, this is the hash function we're going to use in this protocol, and everyone is just using that.
Oh, okay. And then I have another question.
As long as the hash function has the cryptographic properties, I don't think anyone really wants to disagree with a standard hash function. Yeah.
I have a question regarding the attack by the bank. So why can't the bank just, let's say you said if the bank finds a transaction which has an equal hash, why can't they just reuse the same linked list for the remaining transactions? Because the thing is that you just have to verify if the hash is the same, right? So you can just use the remaining ones and sort of link it with
that's a big if, right? If they can find another transaction with the same hash.
Oh, okay. So if they can,
if they can rewrite the history and you will not find out. But
so if not,
we assume they can't do it because the hash is collision resistant.
So basically, if they can't do it, then you just have to, is it keep on trying until, you just have to make sure that the linked list and you have to keep on computing and make sure that in the end, the hash is the same as limit one.
Yeah, so you have to just compare one hash value.
Oh, okay.
You have to make sure that the new transaction that is given to you in its pointer position, it has the hash of the very last transaction that you have accepted.
So basically there are two ways. The first one is to make sure that the previous hash is the same. The previous pointer is the same. The second one is if you're lucky enough to find like a hash which has the same hash value, then you can just reuse the linked list, right? Is that correct? Okay, thank you.
But again, you're never that lucky in the real world.
Yeah. Okay, understood. Thank you.
And again, we are just assuming this, we are kind of trusting our hash functions. And that's a big thing. Like, if someone can break the hash functions, none of these protocols will work. If someone can break, for example, the collision resistance, and that has happened to some hash functions in the past. So that's also why you shouldn't use your own hash function. You should just use the standard hash function that everyone has tried to break but failed.
Okay, understood. Thank you.
Okay, any other questions? Okay, I just want to say one last thing. When you ask your questions in the chat, please don't send direct messages to me, send a message to everyone so that everyone can see. Okay.
Professor, I have a question just for the previous transaction example. That is, how for the consumer to make sure that the transaction I, not necessarily the transaction N, really pointed to the transaction I-1 without checking the whole history. I mean,
yes,
this cannot be guaranteed. The bank may change the content of the transaction and fake the hash value of the next transaction. That is, the transaction I is not pointing to the transaction I-1. And so with the faking hash values, the other things will not change.
But the idea here is that the bank is kind of announcing these transactions one at a time to us.
Yes.
Right. So when transaction I was announced to us, we have checked that it has the right hash.
Yes,
So
but we checked it before. We checked it before.
Yes.
But now it is come to the transaction XN.
Mm-hmm.
And so, for instance, if the bank changed some of the content in the transaction XI, and without changing the value of the transaction XI plus 1, for instance, because they faked the hash value of the transaction XI, how can we make sure, or how for the consumers to find it out?
So again, the thing here is that the consumer can keep track of their own list of transactions, right?
Yes,
and
yes.
in this case, the consumer will have a list of transactions that has valid hashes, so valid hash pointers, but the bank will have a list of transactions that don't have valid hash pointers. For example,
yes.
I to I+1. So if a dispute arises, then the customer can just say, here's my whole list, and this is a valid list, and the bank cannot do the same thing, right? So it's provable.
So the consumer still needs to preserve his own history.
Yes, but the point again here is that every time a new transaction is announced, the customer doesn't have to go through the whole history and just check everything. He can just check the last hash. This is much more efficient. But if there is sometime a dispute, of course, well, I assume they have to go to court and show that.
I see. Thank you. Thank you.
Which one is the right chain? Yeah. Actually, in Bitcoin, what happens is that they don't go to court. There will be no dispute because everyone sees these things and everyone just follows the sequence that has the right hashes. Okay. Any other questions? Great. So I'll just give you an overview of what's going to happen in the next session as well. We're going to talk about another application of hashes, which is called Merkle trees. It's an extension of this idea of having hash pointers. Okay, have a great day and bye. By the way, I'm going to stay in case anyone has any more questions.